Today we are going to be discussing Lab 4. The purpose of this lab is to investigate how falling magnets induces an electrical current in a conductive tube and how these currents create a magnetic force that slows the magnetic's motion. The coded model for this lab helped us replicate the experiment multiple times to see how the interactions changed. The physics fundamentals for this lab include Faraday's law, Lenz's law, and Newton's second and third law of motion. And here are the results from our lab. My predicted results is that the average time would be 0.26 seconds, while the actual average should be 0.25 seconds. And the graph is from the coded model, which you'll see later on. Here's the experiment. For the experiment, I dropped a bar magnet through a tube of aluminum foil and measured the time it took for the magnet to make it all the way through. The average time, was, as you saw, was 0.25 seconds, while the coded time predicted 0.26 seconds. And here's the experiment. The system is the bar magnet, while the surroundings is Earth's gravity, the aluminum foil, and everything around the bar magnet. Here are some important equations for this lab, which include magnetic flux, magnetic field of a dipole, and the magnetic force equation. Here's the code for this lab. First, I initialized the initial conditions of the lab with the initial length, width, and inner radius of the aluminum foil, and then I find the dipole, the magnetic dipole of the bar magnet, and then find the magnetic flux. And then I calculated the current in the loop. In the loop, I calculated the current of the ring using a combination of Ohm's law and Faraday's law together. I then used that to help find the magnetic force, which I then helped calculate the net force with gravity and the magnetic force to help me update the position and velocity of the bar magnet. And here are the results. We had an average time of 0.26 seconds through the loop tube. And as we compare that to our actual results of 0.25 seconds, you see that it's a little bit, the average time is a little bit shorter on the actual results. And that can be due to human error in the experiment, as I could have put a little bit more force on the magnet as it was sent through the tube, or any other human error that could have occurred. And here's the model that the code produced. Now, what if? Our two what if questions. We are asked, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, if the conductor's resistivity were nearly zero, the induced currents would be much stronger, and the magnets would slow down dramatically, possibly even levitate inside the tube, never falling through. And the other what if question asks us, what if holes or slots were cut into the tube? How would this affect the ring's current in your model? Well, cutting holes or slots in the tube breaks the continuous conductive rings, preventing the induced current from circulating, and drastically reduces the magnetic braking effect. Finally, we performed this lab so that we could better understand Faraday's law and study how a falling magnet induces current in a conductive tube, helping to reduce the speed of descent. And the errors in this lab include human error in the experiment, which could have reduced the time, or any other errors that could have occurred. Thank you.